acids and stuff like that. So we have nuclear chemistry. There's supposed to be the good, the bad, and the ugly with these nuclear power plants and nuclear power. So Shelby, what's the good is supposed to be clean power. Well, what's so clean about it? Why? What's the big worry right now, I guess, is what I'm... The whole planet's supposed to be what right now? Warming up. Global warming, right? And I don't know how much you've read on this, but what's the gas that they're really worried about? CO2, carbon dioxide. What is the main source of the CO2 getting kicked into the atmosphere? Yeah, but more specifically. Yeah, I hear burning of fossil fuels, yeah, but it's not cars kick out a lot. Where do we in San Antonio get our electricity? How do they generate it? They're burning what? Coal. Coal-burning power plants. In fact, Texas has some of the filthiest, dirtiest coal-burning power plants in the nation because they're grandfathered in. What's that mean? There you go. It's an exception to any rules. Now, because they were built way back when. They followed the rules back then. Now, they are getting updated, and they put on some really and things, right, in the past, recent past, and they're doing a lot cleaner job. But the point is the coal-burning power plants are the #1 producer in the world of carbon dioxide. So that's why they say, ooh, nuclear power, it's clean, okay? But the bad of nuclear power. Oh, wait, before I back up a little bit. It's clean, well, what's all this stuff then? What is that? It's steam. You can't see carbon dioxide. You can't see these noxious gases. It's steam. It's little tiny water droplets. That's what you're seeing. You see a jet in the air, the white stuff? That's water, right? You can't see the noxious gases. You can't see the stuff that's going to kill you or harm the planet. Okay, but the bad of nuclear power. You have all these spent fuel rods. What do you do with them all? Right? Fair? Yeah. But in whose backyard? Matt's exactly right. Whose backyard? And he's right. Nevada. Here it is. They've been spending a lot of money in Nevada in the, Yucca Mountains, right? These huge, huge storage tunnels, way, way down. Very stable land. It needs to be good for about 10,000 years. And they've got it, they think, in Yucca Mountains. But if you lived in Nevada, would you want this? No. If I lived next to Nevada, I wouldn't want this, right? So it's not, they dug the mines is all. They dug the tunnels. Nothing's in there. So this stuff is still sitting all around. If you have a nuclear power plant, just look at an aerial photo from Google Earth or something. You can see the little nuclear waste being stored around it. They don't know what to do with this stuff. So I think an interesting Google question would be, when is the last nuclear power plant built in the United States? I don't even know if they're building them anymore. They don't have any idea what to do with the waste. Okay? So, but this stuff will become stable in the course of about 10,000 years. And that's what today is about. All right? Well, what's that natural process of going from something that's radioactive to something that's not, something that's stable? Okay. This is called Fiestaware. It says on the bottom. And they sold it about 20, 30 years ago. And at the time, this orange color was all the rave. I guess it looks kind of ugly to me, but that's the big thing what everybody was after. So everyone was buying this. You have the little teacups and that kind of thing that go with it. But now you recognize this sound from the movies. What is this instrument? A Geiger counter. It detects radioactivity. There's little radioactive particles, high-energy particles, coming from this Fiestaware. Okay. So, they stopped selling it, obviously. But what can block radioactivity? Can paper? No, paper can't. Aluminum, how about that? Here's some aluminum foil. Not even close. How about my hand? Well, most of it, right? Superman had a science friend. Science friend built him a suit to protect him from what radiation? Kryptonite. It's Superman, man. He's really strong. This material is on this planet. He built it out of lead, right? Because you've played with lead in lab a little bit. You can polish and stuff. It bends. You can make a suit out of it. So if I find some lead here, right? So you have to wear lead. Definitely blocks radiation, right? Okay. So how do we keep track of this radioactive processes and reactions and things? Well, they're going to have us write nuclide symbols. And all we're really doing is keeping track of the number of neutrons and protons. Because that's all that matters in the nucleus. If something's going to be radioactive or not, you just have to have the right ratio of protons to neutrons. Otherwise, you're not good, right? So let's keep track of them with nuclide symbols. Here's how you write them. The element symbol, well, you know all those, right? Carbon is C. I we know those. How about atomic number? It's from the periodic table. How do you find it? Like in our periodic table, which numbers are they? Yeah, are they numbers on top? Are they the blue ones? They're the blue ones in the corner, right? They're the number of protons. Good. They're the number of protons, right? You get it from the periodic table, number of protons. Right. How about mass number then? The number beneath wasn't mass number, it was molar mass. That's just, right, the mass in grams of that number, Avogadro's number of that atom. It's protons and neutrons. You can't get it from the periodic table. Number of protons plus number of neutrons. Okay? So you can't get that from the periodic table. Here's a question for you. Victoria, let's say, I don't know, sodium. Okay. Victoria, sodium has how many protons? 11 down there. Now, what the number of neutrons is, but usually they're roughly the same as the number of protons. So 11 plus 11 is 22. I'm just going to scribble 22 up there. So in the nucleus, you have protons and neutrons. Flying around, you have electrons, right, Jessica? So one of those little subatomic particles I can change, and I'm going to definitely change the identity of that atom. It's the proton, right? You can mess with the electrons, you still have sodium. You can mess with the neutrons, you still have sodium. But once you change the number of protons, you don't have sodium anymore, right? Okay, let's get into some terminology. How do you name these nuclides? Carbon-13. Well, I'll give you a hint. This one, you would call it sodium at 11, 22. They always give you the element name and then the mass number. So how would you write the nuclide symbol for carbon-13? Sylvia, what would you write? The C. 6. She got that from the periodic table. Yeah. So that's how we're not supposed to say, how would you name it? C13, 6, or whatever. So we'll say carbon-13. That's how you name these nuclides. Now, there are going to be a lot of different reactions. Not that many, like only 4 or 5 of these types of decays. But we need to know what the names and the formulas are of these little common radioactive particles that are being shot off. Okay? So we can write these reactions. And we have to know the formulas in terms of nuclide symbols, because it's a nuclide symbol that helps us keep track of the number of protons and neutrons. Okay, you start with the helium-4 nuclide. Well, it's just helium-4, Nick. So definitely, where would you put the 4? At the top. Then everybody, the atomic number for helium is 2. That's not so bad. Helium-4 nuclide. Now, I think the only part that you got to remember is the book isn't going to say helium-4 nuclide. This particle undergoes helium-4 nuclide decay. No. It says alpha. It calls it an alpha particle. It undergoes alpha decay. So you got to remember, okay, helium-4 nuclide, you know how to write it, and then remember it's also called an alpha particle. Electron. What particles do they call electrons? Anybody know? There's the B. Beta. Beta particles. So they're going to have a little E for the nuclide symbol there. Now there's no neutrons or protons, so you have a 0 up there. But to keep track of these, what's getting converted to what, neutrons to protons, you have to have a -1 on the bottom. Okay. Very high energy light. This is a symbol. What is that? The Greek symbol. Starts with a G. Gamma, this stuff is really high energy, right? You hear, oh, solar storm, gamma radiation is going to hit the Earth. There's no neutrons or protons, so everything's 0. Just energy. Positively charged electron. Okay. They're going to call those positrons. And, well, yeah, the positively charged electrons, it exists. You have the E, no neutrons or protons, but instead of a -1 for the mass number, you're going to, for the atomic number, you can put a +1. Help you keep track of protons and neutrons getting interconverted. Neutron, they want you to use a little n. There aren't any protons, but 1 neutron, so the mass number must be 1. That's not too bad to remember. It's kind of common sense. The naming isn't. I mean, why not come up with a fancy name for a neutron? But they didn't. Okay. So know those formulas and books' descriptions of those particles. And if you know those formulas, balancing these nuclear reactions aren't bad at all. Because all you got to do is make sure the superscripts add up to be the same number on both sides. Make sure the subscripts add up to be the same on both sides, right? Make sure the mass numbers add up to be the same on both sides. Make sure the mass numbers add up to be the same on both sides. Okay? So if that's the case, what must the mass number here be? Adrian, what would you say? 18. It's got to be 18. Everybody, how about the atomic number? It's got to be 8. All right. So that means I have an 18 for a mass number, an 8 for atomic number. What's the symbol have to be? Has to be oxygen. There's our answer. Okay. That's not that bad. Now, why does all this radioactivity occur in the first place? Well, the book gives us something called the belt of stability. But, Jasmine, it simply comes down to a nucleus is radioactive or stable, depending on the ratio of protons to, what'd you get? Neutrons, right? That's all that matters. The proton to neutron ratio, right? So, how do you read this belt of stability? To me, that belt of stability should be a little more descriptive. It's these dark red dots. Right? That's really that belt of stability. Okay, that's the very center of it. Okay? And so if you're going to read this graph and recognize, right, here's neutrons, here's protons. So, Vanessa, if we have a nucleus with 20 protons in it, you need about how many neutrons to be stable? using this delta stability plot. If you have about 20 protons, that means we're right here. You need about 20, right? It's really close to 20. 20 neutrons. What if we have about, Ray, how about 80 protons? Then you need about how many? What would you guess? Probably around
110.
All right. Ray, what do you think? Keep going up so you hit the delta stability, and then go over. Seems to me it's pretty much nailing that 120 about, isn't it? Okay. So it looks like the bigger these atoms are getting, the more what you need in the nucleus, the more neutrons for it to be stable. Okay. And if you don't have that right ratio, you're just going to undergo those different types of emission, those different types of radioactive decay to get into the delta stability. In fact, if according to this delta stability, if 80 is right about here, it looks like it stopped right around here. So that means nothing above, I don't know, whatever number that is, 85, 80, it's somewhere a little over 80, right? And if you look at the periodic table, it's got to be bigger than 82, because we know lead's not radioactive. So, I don't know, 84, 83, somewhere around there. You're right, right? Okay. I don't know, 85, somewhere around there. But it's got to be bigger than 82. Common nuclear decay reactions. Here they are. I wouldn't memorize these things at all, because we already know these little particles, right? If they say, that means beta emission and positron emission. You just have to write that particle as a reactant or a product. If they use the word emission every single time, write it as a product. It's getting produced. That's all. So just read the question careful. Oh, it's undergoing alpha emission. I'll just write an alpha particle on the product side. Right? The only one that's going to change, electron capture. Now you have to write an electron as a reactant. So just read it careful. Right? I don't think there's anything really to memorize there. Let's try this example. Fill in the blank for each decay reaction above if, Matt, how do I name this? How do I name this nuclide? What? CO is cobalt. Cobalt 60, right? So fill in the blanks for each decay reaction above if cobalt 60 undergoes that type of decay. So I better write Jessica Rojas cobalt 60 in every single one of these reactions as a reactant or a product. The reactant, it's undergoing the decay. It is decaying. It's falling apart. It's decomposing. So you better write it over here every single time. All right. There. Okay. So go ahead and determine what the missing product is. Right? Remember the name of the game, just make sure the mass numbers add up to be the same on both sides. Make sure the atomic numbers add up to be the same on both sides. We'll give you a few minutes to do it, then we'll ask around, see what you got. Not sure, just ask. You have to add, make so, like for this, let's do this one. So for this one, 60 has to add up to be both of these. So this has to be a well, let's figure it out. This has to be what mass number? 56, right at 56. And then the atomic number has to be 25. So what has 25 protons? Yeah, look at the periodic table. All right? Let's make sure you're... All right, this has to be a 56. This guy has to be a 25. Right? So, what the heck is 25? You think I'd know this by now, right? How many years I've been doing this? Manganese. Thanks. So do the same thing for all of these. It must be manganese 56 for the first one.
Yeah.
Okay. Let's ask Alexa. Now, Alexa, when you give me the answer for the second one, name it the right way. For example, the first one is manganese 56. So how would you name this one right here? She says nickel 60. Does everybody agree? So what's the atomic number on nickel? Is it 28? Yeah, it's 28 and negative 1. Okay, that works. How about the next one? Lewis. What one? The right? Iron 60. Everybody agree? So it's got to be 26. Okay. Pablo. He says cobalt 60. Nothing changed. Right. Last one, Mariella. What's that? She says iron 60. So that means this guy has to be 26. Yeah, that works, right? Everybody agree? Okay. Write the nuclear equation for the decay of phosphorus 32 to sulfur 32 by beta emission. So they want you to write the balanced radioactive decay reaction for that process. Decay of phosphorus 32 to sulfur 32 by beta emission. So remember, know what a beta particle is? Definitely write it on the product side. That's where I would start. Oh my God. Thank you. Okay. Oh, beta, that was this thing, right? That was an electron. Phosphorus 32. Sulfur 32. What the heck? What's the atomic number of phosphorus? What did you come up with? 16? So that means this guy's 16? All right. Everybody agree? All right. So let's go ahead and I think we're all on the same plan here. Work on these three, then we can call it a day. Now that last one I think is a little. I think that last one's tough. See if you can knock these out. Talk to the folks around you. They didn't need it. What's that? Really don't. You just need to know the names of the particles. Yeah. Oh, to get into the belt of stability. So that, and the point of the reaction is so that we can keep track of the number of protons and neutrons. That's all. Using, and that nuclide symbol does it. SC. Oh, I should help you. I had to Google curium. When you get to that one, it's CM. Which one are you looking at? Mass number, right? This total mass number on this side has to be 30. The total on this side has to be 30. A 3, because you have 3 and 27 to be 30. So that must be a 3 for a mass number. I don't know. What's the atomic number? This one is 14 total. So this one has to be 14 total. It should be a 2. So what has 2 protons? Yeah. Yeah. So that has to be 3. The atomic number has to be what? This side is 14. This side has to be 14. So it has to be a 2. So what has 2 protons? No, that's right, because 3 and 27 is 30. 13 is 14. That's 14. That's right. And then you need a single positron. 1. That's right, yep.
equal what was the first, what was the first element?
Let's see. You have to form a neutron and curium-242. And then mass numbers and atomic numbers have to be the same on both sides. Oh, yeah, what has to be on the reactant side? Yeah. Yeah, because they were bombarding it with it. Right? So this isn't uranium, right? That's not... What was the target element? It's not Pu. It's that thing. That whole... Because you're not giving a complete answer with this. It needs to be that whole nuclide symbol.
So in this, so in 2025, the alpha particle relevant to the question?
No, it has to be in your reaction. Yeah. So that element, what you're after, plus an alpha particle, right? Because it collides into it, and then it's going to form those products. Where's scandium? I can't find for the life of me. Oh, it's 21. Thank you. All right. So I need, what, 20 here?
No. Wouldn't it be 94 over 239? The 94 is PU.
Yeah.
There it is. There you go.
Okay, let's see if you guys have a consensus on this last one. Everyone should be working on it, I think, by now, it seems like. So let's first put in the parts that you know. Where are you going to put the alpha particle? How do you know?
Because it gives you the product.
Bombarding. Yeah, that's how I see it too. There might be another way to see it, but bombarding. So you're bombarding with an alpha particle. But definitely put that here. What else do you know? That you know the two products. Exactly. You know one's a neutron, and you know the other one is this curium-242. And we said curium was it's 90. Thank you very much for finding that. 96, 242. So that should give you enough information to figure out what the unknown element is. Right? Make sure the mass numbers are the same on both sides, atomic numbers. So what the heck? 242 and one is 243. 239, right? Because 239 and 4 would be 243. And 94. So she says P. Well, now what is Pu? Plutonium. Yeah, plutonium. Okay. So have a good weekend.
During lab is when our review is.